Self-driving cars. They're not some distant dream anymore. They are right here, on our roads, navigating our cities. But have you ever really stopped to think about what's going on under the hood? It's not just an engine, it's a mind built completely out of code, and it's making life-or-death decisions every single second. So let's pull back the curtain and see how that mind actually works.
So take a look at this glowing, pulsing image. It's a 3D point cloud from a LiDAR sensor. It's like a digital ghost of the world around the car. But turning all that abstract data into a real decision, hit the brakes for that pedestrian or swerve to avoid that cyclist, that is an incredibly complex journey. And it brings up the real question here. How does this machine mind work? And should its code be a secret?
All right, so to understand this artificial mind, we've got to start where any mind does, with the senses. Before a car can think or act, it first has to see. It has to perceive its environment in just meticulous detail.
A self-driving car's senses are really its network of super high-tech sensors. And it's not just one type of eye. Think of it more like a whole team of specialists, all working together. Each one has a unique way of seeing the world, and their combined goal is to build a complete 360-degree digital picture.
And each sensor here has its own superpowers and its own kryptonite. You've got LiDAR, which paints those incredible 3D maps but gets basically blinded by heavy rain. Then there's radar, which is a champ in bad weather, but it can get thrown off by interference. Cameras, they're cheap, and they're essential for seeing color on traffic lights, but they really struggle in low light. And finally, Ultrasonic is super accurate for parking, but it's totally nearsighted. The real key here isn't just that they have trade-offs, it's that this creates a system of redundant, layered safety. Each sensor's weakness is covered by another's strength, making the car's total perception way more robust than any single sense could ever be.
But okay, all that sensory data is really just noise without any context. So the next step is to turn that raw information into a coherent picture. The car has to build a map, and not just of the city, but of its immediate surroundings, right now, in real time.
This is where a process with a really fantastic name comes in, SLAM. It stands for Simultaneous Localization and Mapping. Now, think of it like this. Imagine you're drawing a map of a room you've never seen before, while at the same time, you're trying to pinpoint exactly where you are on that map as you're drawing it. That's SLAM. The software is constantly identifying landmarks that don't move, a curb, a street sign, the corner of a building, and uses them as anchors to constantly refine both the map and the car's position on it. It's this continuous loop of see, map, locate, repeat.
And this is exactly why SLAM is so critical. Without it, the car is effectively lost. Yeah, it might see a tree, but it has no idea if it's getting closer or further away, or if it's even the same tree it saw a second ago. SLAM provides a persistent memory of the world and its place in it. Honestly, it's the absolute foundation of navigation. So our car can see, and it has a sense of place. But how do we actually teach it to drive safely? I mean, you can't just hand it the keys, right? It has to go to school first. A very advanced kind of school. Welcome to Driver's Ed for Artificial Intelligence. Before these cars ever touch a public road, they are trained and tested in these hyper-realistic virtual worlds. Simulators like Carla and SVL can recreate pretty much any weather condition, any traffic jam, or any bizarre edge case scenario you can possibly imagine. And they do it all in a perfectly safe and controlled environment. And the scale here is just staggering. Companies like Waymo have driven their vehicles for over 10 billion miles in simulation. To put that in perspective, that's an amount of experience a human could never, ever achieve in 1,000 lifetimes. This is how the AI learns to handle situations it might only see once in 1,000,000 miles of real-world driving. Okay, so this brings us right to the heart of the matter. We've built a machine that can perceive, it can map, and it can learn. It has a mind. But the conscience of that mind, well, that's its code. And that leads to a huge debate. Who should get to look at it?
This slide really lays out the two opposing camps. On one side, you have the open source world, with projects like Comma.ai's OpenPilot. Their philosophy is basically, many eyes make all bugs shallow. The idea is, by letting everyone see the code, a global community of security researchers can find and fix problems super quickly. It's a reactive approach. And on the other side is the proprietary or closed source model, which is what traditional automakers love. Their philosophy is security through obscurity. Keep the code a secret and trust that your dedicated internal team will find all the bugs before it ever gets out. It's a proactive approach.
And this quote about the Volkswagen emissions scandal, wow.
It's such a powerful, real-world example of the risks that come with closed systems. Volkswagen was able to hide code specifically designed to cheat on emissions tests precisely because no one from the outside could inspect it. That deception was only discovered after tons of painstaking, real-world testing. Now, with an open-source system, a piece of code like that, it would have likely been spotted almost immediately.
So, which is better, the security of a secret vault or the wisdom of a crowd? Well, the path forward might not be about picking one over the other. It might be about establishing a process that ensures safety and builds public trust, no matter which model you choose. So instead of just a one-time security check, the industry is moving towards this continuous, cyclical approach to safety. One really established framework for this is called the Threat Intelligence Lifecycle, which is a formal process for constantly identifying, analyzing, and dealing with potential threats.
It's this 6-step loop. You plan what you're looking for, you collect the data, you process it, you analyze it for threats, you share your findings, and, most importantly, you use feedback to start the whole cycle all over again. Now, here's why this matters to our debate. Whether the code is open or closed, adopting a rigorous, transparent process like this is absolutely essential for building public trust. It shows that security isn't just a one-time goal, but a continuous process of improvement and vigilance.
Which brings us right back to that central question. As we hand over more and more control to these incredibly complex systems, we have to decide what our priorities are. Is safety best achieved by locking the code away and just trusting a small group of experts? Or is it better to open it up to the entire world, believing that a global community will ultimately make it stronger? The answer to that question is going to define the future of how we move and how much we trust the machines that move us.